Hello everyone, my name is Thomas Cohn and I'm here to talk to you about motion planning. If we look at motion planning today, most techniques can be divided into two main categories. The first is sampling-based planning. It relies on drawing random samples from the configuration space and connecting them into a graph structure. Graph search is well understood, and we know we can get global probabilistic completeness, but the number of samples required can grow exponentially with the dimension in the worst case, and these techniques struggle to produce smooth paths or handle dynamics. The second main category is trajectory optimization. By encoding the motion planning problem in optimization form, it's possible to add all manner of costs and constraints, making it straightforward to handle dynamics and produce smooth paths. Such methods also scale well with dimension, but the problems are inherently non-convex in all but the simplest cases, so global optimality, or even feasibility, is far from guaranteed. We want to get the best of both worlds, and then some. That is, we want to compute smooth, globally optimal paths in high-dimensional configuration spaces. To handle this, we look to a common challenge for both methods: collision avoidance. One of the main sources of non-convexity in trajectory optimization is the presence of obstacles, as constraining a path to lie outside of a collision set, such as the red region in the figure on the left, is generally non-convex. Instead, we can cast such a constraint as contained within a convex safe set, such as the blue regions. This allows us to guarantee that a whole trajectory is collision-free, simply by checking its control points. And now, with many regions, one needs to combine all of these trajectory pieces into a single path from the start to the goal. A recent framework called the Graph of Convex Sets, or GCS for short, has shown great promise for this purpose. GCS transcribes the problem as a mixed integer convex program, but we have a line of work that shows that in most cases, we can just solve the convex relaxation in order to get high-quality paths. However, because GCS leverages convexity, it's naturally restricted to a Euclidean space, whereas many robot configuration spaces are non-Euclidean, and this is where our work comes in. As an example, consider a robot with two revolute joints, both with no joint limits. Such a configuration space is best represented as a smooth manifold, specifically a torus. Calling this configuration space Q, we turn our attention to M bar, the collision-free subset of the space. We can then describe the general form of the motion planning problems we're interested in. Breaking this optimization problem down, we want to find a path gamma so as to minimize arc length. We require gamma be piecewise differentiable. And finally, we specify the start and goal points. Of course, this is a very abstract problem statement. To actually solve it, we first generalize the original GCS framework to function on manifolds through the language of geodesic convexity. Then, we describe a transformation procedure to move everything from the manifold back into Euclidean space, yielding a GCS-style problem. And finally, we add an additional requirement on the curvature of the space in order to ensure the resulting problem is indeed convex. Now, let's actually put this framework into action by constructing whole-body plans for a PR2 robot. It has a 16 degree of freedom configuration space to plan through, including a mobile base and multiple revolute joints without limits, all of which can potentially wrap around in the wrong direction. For example, with standard nonlinear trajectory optimization, choosing the wrong angle value modulo 2 pi can lead to results such as this. Clearly, this is far from the optimal path. An ordinary GCS is not immune to this problem. As shown here, it exhibits similar behavior. However, our extension is able to gracefully handle the wraparound. I want to emphasize that we're obtaining an elegant, globally optimal motion plan for a 16 degree of freedom system with strong collision-free guarantees. With the confidence that our technique will always choose the right direction, we can put it into practice for multi-query planning. In this case, for a Kuka-Iwa arm, modified to remove joint limits from its base joint. As the arm moves the mugs around the shelves, it never goes the long way around and always produces high-quality trajectories. And with that, I'll conclude this presentation. Thank you.